Hi, class. We're here for extra practice for quiz 4. I have a bit of a head cold, but calculus continues. So the first question, we want to differentiate each function. Do not simplify. Okay, letter A. Fundamentally, what I see is one function times another function. So we will use the product rule. Y prime, we have first times, well, the derivative of the second. Really, this is a chain rule. We take derivative of the outside, evaluate it at the inside, times, well, the derivative of the inside function, which is pi. Okay. I'm not finished. So far, I have first, derivative of the second, and then we put a plus, and we just copy the second. Okay. When I go to take the derivative of the first, this is another chain rule. We have derivative of the outside, evaluated at the inside, and then times the derivative of the inside function. So here is our derivative of y. Next question, g of y. Fundamentally, I have an inside and outside function, so this will be chain rule, g prime of y. Here's the derivative of the outside. Put in the entire inside function, e to the minus 4y plus 8. Now we have to multiply by the derivative of the inside function. When I go to differentiate e to the minus 4y, this is chain rule. So e. So far, I have derivative of the outside evaluated at the inside, and then times the derivative of the inside function, which is -4. Maybe I should underline. There's my first answer, and there's my second answer. Letter C. Here we have ln absolute value in the question. We discussed this derivative in class, and one thing I mentioned is when we get to integration, this will be an important derivative rule. Okay, so this is a chain rule. We have 3 times. Well, when we differentiate ln absolute value of x, we have 1 over x. So derivative of the outside looks like this. Then we put in the entire inside function, which is sine x plus cosine x, multiply by the derivative of the inside function. Derivative of sine is cosine, and the derivative of cosine is negative sine. You could move this into the numerator if you'd like, but I'll leave it as is. Number 2. Find an equation of the tangent line to x to the 2/3 plus y to the 2/3 equals 5 at the point 8, 1. So the first step in implicit differentiation is we differentiate both sides of the equation, understanding that we're thinking of y as a function of x. Very nice. So I have 2 over 3, x to the minus 1 over 3 plus 2 over 3, y to the minus 1 over 3 times dy dx. That is an important part we don't want to leave off here. And then equals, well, when we differentiate 5 with respect to x, we just get 0. Derivative of a constant is 0. Now I need to do some algebra to solve for dy dx. So I have 2 over 3 y to the minus 1/3 dy dx equals negative 2 over 3 x to the minus 1/3. You notice I could divide both sides of the equation by this 2/3. And then we can multiply through by y to the 1/3. The left-hand side becomes dy dx. The right-hand side, I have this minus. I have y to the 1/3. And then really this x to the minus 1/3 is in the denominator with a 1/3 power. So it'd be like this. And then I'll do one more step here. This is negative y over x to the 1/3 power. Well, I'm not finished here. I need an equation of the tangent line. We already have the point, which is on my graph and on my tangent line. It's 8, 1. And so to get the slope of the tangent line, we can just evaluate dy dx. At this point, I get negative y over x to the 1/3. 1/8 to the 1/3 power is 1/2. So I have negative 1/2, negative 1/2. This is the slope of my tangent line. Maybe I'll write this. This is my slope. So let me highlight. We have a slope. We have the point. Now we can just write down the equation or an equation. Y minus 1 is negative 1/2 x minus 8. Number 3, use implicit differentiation to find dy dx. Okay, 3x squared plus 3y squared times dy dx. This equals, now if you stare at this, 5x times y, this will be product rule. Here we go. First times, well, the derivative of the second, derivative of y, this is dy dx. So first derivative of the second plus the second times, well, the derivative of 5x with respect to x is 5. So I've differentiated everything inside here. My next step is move everything with the dy dx on one side and everything without to the other. Okay, so I will have 3y squared minus 5x dy dx equals, this will be 5y minus 3x squared. My final step in solving for dy dx is we just divide by this. So we have dy dx equals 5y minus 3x squared divided by 3y squared minus 5x. Okay, here comes another one. We have x e to the y equals x minus y. Now, this side of the equation is product rule. When we differentiate everything in sight, we have first derivative of the second. Well, the derivative of e to the y with respect to x is e to the y times dy dx. First derivative of the second, and then we put a plus the second times the derivative of the first. So here was our product rule. Okay, when we go to differentiate the right-hand side, we have 1 minus dy dx. At this point, we have differentiated both the left and the right-hand sides of the equation. So I bring all the terms with dy dx to one side of the equation and all the terms without dy dx to the other. Here, I get x e to the y plus 1 dy dx equals 1 minus e to the y. Now, final step, we divide both sides of the equation by x e to the y plus 1. dy dx is 1 minus e to the y divided by x e to the y plus 1. Number 4, given x squared is natural log of xy. Calculate dy dx 2 ways. First, implicit differentiation. Now, I'm going to make my life a little bit easier. You notice natural log of xy, when we have a product inside of the log, turns into a sum. So I can just rewrite this equation as x squared is ln x plus ln y. Maybe I'll make this a different color. I haven't differentiated anything yet. I've used a log property, well, one of them that we reviewed the first week of class. Okay, this will make the differentiation process a little bit easier. For the left-hand side, I have 2x. Now differentiate the right-hand side. We have 1 over x plus 1 over y times dy dx. This was much simpler because I used a log property first. All right, so 1 over y dy dx equals 2x minus 1 over x. Now to solve for dy dx, I can just multiply through by y. Dy dx equals 2xy minus y over x. Letter B. Let's do this extra / wonderful practice problem. We will calculate dy dx by explicitly solving for y first. And note that the formula will look a little different than this, but it's wonderful practice of some of the rules for derivatives that we practiced on the first page. Okay, what I can do to solve for y first, I'm going to work with this equation and take e to the on both sides. The left-hand side will be e to the x squared. The right-hand side, we know e to the ln of something, well, is the something. So here, e to the ln of xy. Let's see, I'll write it in highlighter. This is xy, so that goes here. We can divide by x. We get y is e to the x squared over x. So now you see, this is a nice exercise in rules for derivatives. So to find y prime, or dy dx, we have denominator times the derivative of the numerator, which is a chain rule. Derivative of the outside evaluated at the inside times derivative of the inside function. Denominator, derivative of the numerator minus the numerator. Derivative of the denominator is 1, and then all over the denominator squared. That was fun. Next, we are now in 5.1, which involves critical numbers. It involves intervals of increasing and decreasing. Show that h of x is x over x plus 5 has no critical numbers. What are critical numbers? These are x values in the domain such that the derivative is 0 or does not exist. If you want to begin this problem, we can think about the domain. We did this kind of thing first week of class. We cannot divide by 0. So the domain is minus infinity to minus 5, union minus 5 to infinity. Wonderful. Now, let's calculate the derivative. This is quotient rule. Denominator times the derivative of the numerator minus the numerator times derivative of the denominator all over denominator squared. So let's take one small step to simplify this. I have x minus x. So my numerator is this. 5, and my denominator is x plus 5 squared. Wonderful. Well, critical numbers, x values in the domain such that the derivative is 0 or does not exist, just like I said moments ago. So we can think about, when is the derivative 0? When is the derivative does not exist? We have to think about how this works with fractions. So a fraction is 0 only when the numerator is. This would say 5 equals 0. Okay, never. So the derivative is never 0. The derivative does not exist. A fraction does not exist when the denominator is 0. But this would say x plus 5 squared is 0. This happens at minus 5. But this is not in the domain. Therefore, well, we don't have any critical numbers. We have finished number 5. Number 6. And this is the last one. We want to find critical numbers for f of x and open intervals where f of x is increasing and decreasing. Maybe before I start calculating the derivative of f, we can think about the domain. F of x is a polynomial, so my domain is all real numbers, minus infinity to infinity. Wonderful. Now, take the derivative. Power rule. Here we have 3x cubed minus 15x squared plus 12x. Generally, we do not need to be able to factor cubics, but this cubic is x times something, so we can definitely factor this one. In fact, my strategy is always factor out what's common to every single term. In this case, every term has 3x. So I have 3x times x squared minus 5x plus 4. I need two numbers that multiply to positive 4 and add to negative 5. How about minus 4 and minus 1? Let's check. We multiply positive 4, we add negative 5. So my derivative is 0. Well, it happens at 3 values. It happens at 0, 1, and 4. And note that the derivative exists everywhere. So the D and E part of critical numbers doesn't come into play in this example. Letter B, find open intervals where f of x is increasing and decreasing. I typically make a number line here. We have 3 critical numbers, 0, 1, and 4. Then I'll usually write my open intervals underneath. So this one goes minus infinity to 0. We have 0 to 1. We have 1 to 4, and then 4 to infinity. Now, I need the derivative here, so I'm going to use it factored because it makes my life a little bit easier. I make a little chart where I'm going to test a point in each open interval. Let's see, I can test minus 1, I can test maybe 1/2, I can test 2, and I can test 5. Let's write them down. We will test the derivative at minus 1, 1/2, 2, and 5. It's okay if you want to use your calculator to evaluate the derivative at these, but I typically will use the derivative factored because I can think about the signs kind of quickly. At minus 1, this is negative. Minus 1 minus 4 is negative. Minus 1 is negative. So my derivative, I have 3 negatives. This will be negative. At 1/2, 3x is positive. This one's negative. This one's negative. 2 negatives multiplied give us a positive number. At 2, 3x is positive. X minus 4 is negative. X minus 1 is positive. 1 negative gives us a negative number. And at 5, we have positive, positive, positive. You multiply three positive numbers, this is positive. So we can put these signs underneath. Maybe I'll make them thicker. This goes minus, plus, minus, plus. Now I can just read off my conclusion. My function is increasing everywhere I see a plus. So this will be 2 open intervals. This will be 0 to 1 and 4 to infinity. And then my function is decreasing everywhere I see a minus. This will be minus infinity to 0 and 1 to 4. So this completes this last question on our quiz extra practice. Thank you so much, everyone.